Swayam Prabha. Digital India. Educated India.
Hello, welcome everyone to this series on the modeling of multiphysics system. So today is lecture number 4, and we will start by finishing and covering the part of the dimension analysis which we had started in lecture 3, and we'll move on towards numerical methods. Okay. So in the last lecture we had looked into the aspects of dimension analysis. How an equation, either a linear, nonlinear equation or a differential equation, which is composed of one or more variables and could be decomposed into something which is simplified, something which is reduced down to the values in the range of 0 to 1. This analysis we call dimension analysis, in which we selected dimensions based upon the variables and a sense of a measure of a value. Say the displacement of a ball that is being projected. We are trying to model the displacement. So we have an idea of how much the displacement can be there. Based on that sense, we are normalizing these equations and then trying to solve it. We have also seen that the selection of a variable and the selection of the normalizing, it does not affect our differential equation. We can select normalizing based upon length, mass, we can select normalizing based upon density and time or any other parameter. The overall equation or the values within the equation, it remains the same. However, the nature of the equation does show a different type of equation. So you can get a linear expression, you can get a quadratic expression. However, if you compare the two expressions, the normalizing variable still remains the same. All right. Now we will take up one example and with which we will finish this segment of the dimension analysis, in which we will see that how selection of these normalizing variables do affect our solution process by taking this rocket projection example. So let's take that we have a rocket, an image is shown over here, in which the rocket is moving up. The force on it with which the rocket moves up is F is equals to mass times acceleration. So force is equals to mass times acceleration. Now acceleration is the second derivative with respect to position. So dx squared by dt, d square x by dt square along the direction of projection, that is, say this is the z direction, so along Ez. Now, what is this countering against? This is countering against the acceleration due to gravity. So, the acceleration due to gravity Fg and the force on the rocket with its mass is mg, the g vector. So, that is mass times g into minus Ez. So, if you compare these two forces, so F vector is equals to Fg vector, or we can say md square x dt square is equals to minus mg, and we can cancel out the m's. So, d square x by dt square is equals to minus g, right. So, this is our differential equation. Now, this is a second order ODE. We will talk about ODEs more when we solve the ordinary differential equations. So, this is a second order ODE, and how many boundary conditions would we need, or initial conditions we would need? So, we need two initial conditions. This is a time derivative. So, two initial conditions are needed, and these would be that at x, that is position at time is equals to 0 is some value, say it is on the flat surface, so that is 0. I am messing up with the directions. Let us take these as x. So, we will be consistent with directions Ex. And say the velocity at time t is equals to 0 is some velocity v. So, this is our launch velocity. Now, the rocket is moving up. We can solve this differential equation. So, integrating once, we get dx by dt equals to minus g of t plus c1, and then integrating again. We will get x is equals to minus gt squared by 2 plus c1t plus c2. So, this is our x expression, and we will use our initial conditions to get c1 and c2. Okay, let's go to next slide. So, if we put at t is equals to 0, x of 0 is equals to 0, that is minus gt squared by 2 becomes 0, c1t becomes 0, we will have c2, which implies that c2 is equals to 0. Again x dot at 0, what is x dot? X dot is minus g into t plus c1 is equals to some velocity v, which implies that c1 is equals to v. So, our expression x of t will be equals to minus 1 by 2 gt square plus vt. This is our final expression. We can therefore find x, that is our position, as a function of time, and which is driven by the acceleration due to gravity and the launch velocity. What is the maximum height? So, the maximum height the rocket can reach is we need to find x max. So, we can take the first derivative dx by dt, it is minus gt plus v, we make this equals to 0. So, the time required to reach the maximum height is v over g. So, if we substitute this time in our x at t max, we can get, so 1 by 2 g into v by g whole square plus v into v by g, we will get v square by 2 g as the maximum height. This is equals to x max. All right. So, this was our flat surface problem. So, we had a flat surface from which the rocket was launching. We balanced out the gravity, force due to gravity by the acceleration of the propulsion, and we found out an expression for x as a function of the acceleration due to gravity and the launch velocity. This was quite straightforward to solve. Now, if we take another case, say case 2, and in the last slide we can say this is case 1. So, say this was case 1. So, in this case 2, consider that the earth is curved, and the earth is curved. So, we are now taking the curvature of earth in reference. Our force due to gravity, and let us keep our analysis scalar, mass of earth into m divided by x plus r square, where x is comparable to r. Okay. So, now the rocket is being launched, and x, that is the distance from the surface of the earth of the rocket, say this is the earth's surface from the center, this is r, and say the rocket is over here, then this distance is x. Okay, this distance is r. So, from the surface of the earth, we have projected x up, and the radius of the earth is r. So, gm em by x plus r whole square. Okay. So, at the surface where x is equals to 0, our force due to gravity is equals to gm em by r square. Okay. This is equals to mg, where g is equals to gme by r square. Okay. So, we can get g out of this is the capital G, that is the gravitational acceleration, into me divided by r square. Okay. Now, let us substitute this back into our expression. So, our force due to gravity, we can multiply and divide by r square. So, we will have g m e over r square into m into r square over x plus r square. Okay. This is equals to m into g r square over x plus r square. Okay. So, we have remodeled our expression. We do not have just mg anymore, we have now a nonlinear term driving this equation. So, upon force balance, so if we balance this force against the launch force by the rocket, so we had our expression m d square x by dt square, which was upwards, means it was propelled upwards and gravity is pulling downwards, equals to minus mg r square over x plus r whole square, or we will get our expression as d square x by dt square equals to minus g r square over x plus r whole square. Okay. Again, this is an initial value problem. We will need two initial conditions. We can have the same initial condition, x of 0 is equals to 0, that is on the surface, and x dot of 0 is equals to the velocity, that is our launch velocity. So, these are our initial conditions. Now, this second case we can try to solve using two types of normalizing parameters. So, the first, so we try to normalize this ODE by two case study. Case 1 or case A, we are normalizing with the length of the earth or the radius of the earth. So, normalize with respect to r. So, our x bar will be x by r and our t bar will be equals to velocity into t by r. Okay. But it means is that our length parameter is r and our time parameter is radius over velocity. Okay. So, let us substitute this into our governing equation. Now, let us write down our governing equation one more time. D square x by dt square equals to minus g r square over x plus r whole square. And our initial conditions were x 0 and dx by dt at 0 was equals to the velocity v. So, on substituting, maybe you give it a try first. Okay. So, if you have paused the video and try to give it a try, we can quickly do this. So, this is r from this x and then the velocity term will be r by v whole square d square x bar by dt bar square will be equals to minus g r square over r x bar plus r whole square. So, we can take out r common from here, this will be minus g 1 over x bar plus 1 whole square. Okay. Let us simplify this further. We will have v square by r d square x bar by dt bar square equals to minus g 1 plus x bar whole square. We can bring this g to the left hand side and make this term as epsilon. So, let us define epsilon equals to v square over rg. So, what is epsilon? Epsilon is a sense of the square of the velocity. It is also called the terminal velocity, square of the terminal velocity ratio. So, in this case the terminal velocity is square root rg. So, you can say that epsilon is a ratio of the launch velocity square to the terminal velocity square. Okay. So, our expression becomes epsilon d square x bar by dt bar square equals to minus 1 over 1 plus x bar whole square. Now, initial conditions become x of 0 is equals to 0 and x dot of 0. So, we can say x dot is r over r by v is equals to v, which implies x dot bar x bar, which implies x bar dot of 0 is equals to 1. So, this is our initial conditions. So, if you want to solve this differential equation, we will have epsilon d square x bar by dt square equals to minus 1 by 1 plus x bar whole square. Okay. So, looks simple enough. We can solve this. This is a nonlinear equation. We can, however, solve this using numerical methods. We will come across how we solve this using numerical methods in the upcoming section in today's lecture. However, just keep in mind of one thing: if our launch velocity is much smaller than the terminal velocity, and the terminal velocity is typically in the range of kilometers per second, right. So, our launch velocity can very well be much smaller than the terminal velocity. In that case, epsilon is less than 1, and our equation becomes, so our differential part will be gone because epsilon tends to 0, and our equation will be 1 over 1 plus x bar whole square will be equals to 0. Now, this expression has no solution, and we cannot solve this because 1 by x bar square, anything square is always positive. 1 by anything always positive can only be 0 if the denominator becomes very large. So, at x bar tending to infinity, at that case only this problem will converge to 0. So, we do not have a solution for this. That means that our assumption, of normalizing our x with r was not a good approximation for x less than r. So, if x is very small compared to r, in which we can consider that as a flat surface and neglect the radius, under such situations if you normalize x with r, x will always tend towards 0. If x always tends towards 0, in that case 1 by 1 plus x bar square will never reach 0, and we will never have a solution by this method. So, we can take another case. So, we can take case B, in which we try to normalize with the velocity. So, we are trying to normalize with respect to the launch velocity. Okay. So, our length dimension becomes v square by g, and our time dimension becomes v by g. If that is the case, then x bar becomes equals to g into x by v square, and our t bar is equals to tg by v. Okay. If we substitute these values into our expression, so again let us write our expression: d square x by dt square equals to minus g r square over r square plus x r plus x whole square. Let us substitute these values in here. We had x bar was x g by v square, so it will be v square by g divided by v by g whole square, d square x bar by dt bar square equals to minus g r square over r plus x bar into we had v square by g whole square. Okay. We can make again one small substitution. We can take r out from here and divide everything by r square, divide everything by r. So, we take r square out and this will be divided by r. We will cancel out the 2 r square. So, g 1 over 1 plus x bar into a term which looks very similar to epsilon whole square. This term is epsilon like the last time. So, epsilon was the ratio of our velocity square to the terminal velocity square, and our left hand side expression has also modified. So, what do we have? We have v square getting cancelled, g will come to the top. So, we have g d square x bar by dt bar square is equals to minus g 1 over 1 plus epsilon x bar square. These two g get cancelled. So, d square x bar by dt bar square equals to minus 1 over 1 plus epsilon x bar whole square. This is our equation, and our initial conditions can be rewritten as x bar at 0 is equals to 0, and let us substitute. So, we have dx by dt. So, x is v square by g divided by v by g dx bar by dt bar is equals to velocity. So, if you see that these terms gets cancelled at time 0. So, dx bar by dt bar or x bar dot at time 0 is equals to 1. So, our initial conditions normalization remains more or less the same, but our differential equation has now changed. The epsilon term, which was earlier multiplied with this d square x by dt bar square, has now been multiplied to this x bar term square. So, epsilon less than 1 is not a problem anymore. So, we can now say that d square x bar by dt bar square is equals to minus 1. This term will go, epsilon is tending to 0. So, epsilon times x bar will be equals to 0, and this will be 1. So, if we solve this, again our initial conditions are x bar 0 is 0, x bar dot 0 is 1. So, let us solve this. What do we have? We have dx bar by dt bar integrating once is equals to minus t plus c1, then integrating again, x bar equals to minus t squared by 2 plus c1 t plus c2. Okay. Now, if we substitute our initial conditions in here at x bar of 0, this is equals to 0 equals to c2. So, c2 is 0, and x bar dot of 0 is equals to 1 equals to c1. So, c1 is 1. So, we have x bar at t bar is equals to minus t squared by 2 plus t. If we substitute our, so all are t bars, t bar, yes, okay, t bar. So, if we substitute back, so substituting and renormalizing, normalizing our expression, x bar if you remember was x g by v square. So, x g over v square was equals to minus t bar was t g by v. So, 1 by 2 t g by v whole square plus t g by v. Okay. Now, let us take v square g to the right hand side of this expression, and what we will get. So, let us rewrite it again. So, we had x g by v square was equals to minus 1 by 2 t g by v whole square plus t g by v. Taking this g by v square to the right hand side, we will have x 1 by 2 t square g square by v square into v square by g plus t g by v into v square by g. V square gets cancelled, g is remaining, v gets cancelled, g gets cancelled. So, x of t is equals to minus 1 by 2 gt square plus vt, and voila, we have our initial expression of the flat earth problem. So, this was our flat earth problem. Okay. So, if we had started our expression with the correct selection of approximation, and the approximation of normalizing the dimensional constants with the velocity rather than with the radius of the earth, then for small launch velocities and for small projections from the Earth's surface, we could find that the solution is same as the flat Earth or the level Earth problem. However, if the displacements are more, in that case, the same differential equation from the last slide, that is 1 by 1 plus epsilon x bar square, is also applicable. You can just put in different values of epsilon. Epsilon is a ratio of the square of the velocity to the terminal velocity, and we can find that equation. So this is a plot which shows different values of epsilon. We can see that as the epsilon value increases, epsilon 0 is very close to the Earth's surface. As the velocity increases and we are going closer to the projection velocity, we can see that the rocket does not want to come back to the Earth and it wants to fly away. Okay, so we have longer projections for larger values of epsilon. Okay. Therefore, this problem, it helps us in several ways, and if you redo the problem again following the steps that we did, you will be able to now normalize an equation. I went over some of the steps quite quickly, so if you go over slowly how we did these normalizations, if we go back a few slides, if you see how we did these normalizations, x over r, vt over r, how the selections were made, then we substituted x as r into x bar. So d square x by dt square, this is 1x, so an r will come out and x bar will stay inside. This is t square, so we will have t bar square, and this t bar equivalent constant, that is r by v, will come out as a square. If you follow these steps very cleanly and carefully, you will be able to come down to a set of equations that is normalized, that is elegant, and that you can solve. Once you solve this expression, like we solved for this renormalized expression, in that case you will be able to come to an expression in terms of the normalized parameter, that is x bar and t bar. Then you can substitute back the values of x and t, and that is called renormalization or redefining our variables, and you will get back your expression in terms of x and t. The challenging part about these problems is that the selection of the correct variable, how these variables are selected for normalization, and those comes with experience and with practice. So as you would practice more, and we will do normalization in each step. When we will talk about thermal science, we will talk about fluid science, we will do solid mechanics. In each of these processes, we will introduce normalizing variables, and those normalizing variables will be selected based upon an understanding of the physics. So we are not guessing a variable in this case, right? So we will select it properly, and those selections will be our basis of the solution that we are getting. For those who would like to try it out, the rocket trajectory code is written over here. So if you would like to pause quickly and take it up, so you can take it. Then we will go to the next segment. Okay, so we are done with the dimension analysis, and we will go on towards numerical methods. Now, numerical methods is the key component of our study. This segment, it will help you to translate all these equations that we are writing so far, and those expressions we will write in terms of physics-based models into a mathematical expression which you can put into a computer, and the computer will be able to solve these equations. So there are two ways of solving a problem. One is called analytical and one is called numerical. Whenever you would search for publications or you would search for documents, you can either search for analytical solutions in which you are solving the maths equation using theorems, and you are trying to get to the solution that is the exact solution of that variable. However, you can also do the same thing using a computer. Now, computers are very readily available nowadays. You can put in these expressions in a computer, write it in terms of something that the program can understand, a program can solve, and you can get a solution back which is an approximate answer, but that approximation is as good as your numerical technique. Okay, so we will start with linear systems. So a linear system is defined by a set of linear expressions. So in this case, an expression is a11x1 plus a12x2 equals to b1, a21x1, a22x2 equals to b2. So this is a two variable linear system. So, that means that we have two variables in this case. Our variables x vector will have x1 and x2. Our initial a11, a12, a21, a22, they are called the coefficients. So, this coefficient is given by the coefficient matrix. As A, which will be composed of a11, a12, a21, a22. Okay. X is our variable matrix and B is our constant matrix. So, what is B? B is equals to B1 and B2. Alright. So, you can see that this set of linear equation, which just consists of two variables, can also be expressed in terms of a matrix system. If you see that this matrix is 2 cross 2, our x is 2 cross 1. So, a 2 cross 2 dotted with a 2 cross 1 will give you a 2 cross 1. B is also a 2 cross 1. So, you will be able to solve this. Now, we can start by taking up an example of this using a spring mass system. So, let us take an example. So, we have a spring mass system. So, this is a wall. We are connecting one set of spring to a mass m1 and then another set of spring to another mass m2. Let us say this m2 is driven by f2 is a force, n1 is driven by f1, m1 is displaced by u1, m2 is displaced by u2, and the spring constants are k1 and k2, k1 and k2. Okay. So, this is an example of a two spring system. So, two spring mass system, just like our above set of example. So, what we have is that our initial condition is that u1 equals to u2 is equals to 0, that everything is at rest and is at its natural location. Now, we apply some forces and the analysis is steady state. That means that any time derivatives are reduced to 0. So, if we look at mass 1 and we do a force balance, let's draw this mass 1 and then we have the spring and then this second mass effect will be there. This is F1, this is K1, this is K2. So, in this direction you will have a force of K1 U1 and in this direction you will have a force of K2 U2 minus U1. So, by force balance we can say that F1 minus K1 U1 plus K2 U2 minus U1 is equals to 0. This is our equation 1. For mass 2, for M2, we can again draw our expression. So, this is our spring attached to mass 1 and then this is K2 and then we have M2. Again force applied is F2. In this direction we is being pulled by minus K2 U2 minus U1. So, we will have F2, let us take out the minus sign from here, F2 minus K2 of U2 minus U1 equals to 0. So, our expression 2. Okay. So, now we have two equations. What are our variables? Our variables are U1 and U2. We have others are constants. So, K1, K2 are the spring constants, F1, F2 are the forces that are driving these masses. Okay. So, we can rearrange our terms and we can come up with the expression that K1 plus K2 times U1 minus K2 times U2 equals to F1 and minus K2 times U1 plus K2 times U2 is equals to F2. Okay. So, this is what we are solving for. So, solving for U1 and U2. We can make a matrix and set it up. So, in matrix form, maybe you give it a try quickly. Okay. So, if you set this up as a matrix, so K of U is equals to F, where K is equals to K1 plus K2 minus K2 minus K2 and K2. Okay. U matrix is U1 and U2, and F matrix is F1 and F2. Okay, so this is our expression. If you want to find the solution will be U will be equals to K inverse of F. So if you invert the K matrix, multiply it with the F matrix, you will get the solutions for U. Okay, let's take an example. So say for K1 equals to K2 equals to 1 and F1 equals to F2 equals to 1. So let's write our expression. So we will have K1 plus K2 is 2 minus 1 and 1 times U1 U2 is equals to 1 1. If you solve this, you will find out that U1 and U2 will be equals to 2 and 3. Try to quickly put in. So if it is 2, then 2 into 2 is 4, 4 minus 3 is 1, minus 2 plus 3 is 1. So 1 1 will match, and therefore you will have the solution for this. So depending upon the value of K1 and K2, you can have different types of solution. Let's take one more type. So for say K1 equals to 0 and K2 is equals to 1 and F1 equals to F2 equals to 1. So in this case you will have 1 minus 1 minus 1 1 into U1 U2 is equals to 1 1. Try to invert this K matrix. You will find out that this matrix cannot be inverted. So you have no unique solution. For this system. Okay. So our two expressions, it can be written in three ways. So one is that we have a solution like this. Say this is equation 1, this is equation 2, this is equation 1, and on top of it is equation 2. So equation 1, this is equation 2, and then we can have equation 1 and equation 2. Okay, this is U1, this is U2. So the first case in which you have two separate equations and the equations are intersecting each other, in that case this is the solution is unique and defined. So solution is unique and defined. The second case in which both the expressions are overlapping on each other, that means they are the same expression. In that case, the solution is defined but not unique. And the third case in which both the equations are not overlapping but are parallel to each other, that means that they will never intersect with each other. In that case, the solution is not defined. Okay, so we can have, so this is for two expressions and giving us two variables as an output. We can also do this with three expressions and three outputs, four expressions, four outputs, and so on. So the number of variables should match with the number of expressions. If you have more expressions or equations than variables, then it is called overdefined. If you have more variables than equations, then it is underdefined. Okay, now we are trying to model these linear systems. So the method that I showed just now, in which you are inverting the matrix, if you take any current day programming software like MATLAB or Python, they will have an inversion package inbuilt. For example, MATLAB uses a backslash for inversion. So you can use a backslash for inversion and get these solutions quickly. Okay. However, traditionally, and you should understand how these solutions can be obtained. They are typically done by iterative methods. Now I am giving you two types of iterative methods. There are many others which are more accurate or can give you a better solution, but these two are fundamental to understand how these expressions work. And these methods will also be useful when we solve for the ordinary differential equations and the other methods. Okay, so we have our Jacobi and Gauss-Seidel are the two types of iterative method. We will start with the Jacobi method. So our Jacobi method is, say that we have a set of expression a11x1 plus a12x2 plus a13x3 plus a1nxn is equals to b1, a21x2 x1 plus a22x2 23x3 plus a2nxn is to b2, and all the way down to an1x1, an2x2, an3x3, annxn equals to bn. Okay, so we have n variables and n equations that we are trying to solve. So from the first expression we can get x1, from second expression we can get x2. So x1 equals to 1 by a11, and we take everything else to the right hand side, minus a12 x2 minus a13 x3 a1n xn plus b1. x2 equals to 1 by a22 minus a11 x1 a21 I am sorry, x1 minus a23 x3 minus a2n xn plus b2. xn will be 1 by ann minus a n1 x1 minus a n2 x2 minus a nn minus 1 xn minus 1 plus bn. So we can see that each expression for x1, x2 to xn, we are skipping over that term that we are finding. Say for the x1 from the first expression, we have from x2 to xn. In the second expression we are trying to get x2. So we had from x1 skipping x2 to xn. Similarly till for the last expression xn from the last equation, we have x1 to xn minus 1, we are skipping over n minus 1. Now your natural question to come from this is that we do not know any of these variables, right? We do not know x1 to xn. Then how do we go about in getting these expressions? So what the Jacobi method says is that to get all of these x1, x2, xn, we will solve this iteratively. We will start with a guess value and we will substitute that guess value into our expression to get the first iteration. So let's start with a guess value. So start with a set of values x1 of 0, x2 of 0 to xn of 0, which means this is our first or initial guess value. Use these guess values to calculate use these to get the first iteration. So this is equals to x of 0. So you will get x of 1, which is x1 of 1, x2 of 1, xn of 1. Okay. So we have started with the guess value. You can take any guess value. There are certain constraints. Apart from that, you can mostly take any guess value. You take these guess values and you substitute into these set of equations. Right. So for calculating x1 of the first iteration, your x2, x3 to xn, all of them will be your guess values from 0. So let's write it down again. So x1 of 1 will be x2 of 0, x3 of 0, xn of 0. x2 of 1 will be x1 of 0, x3 of 0. So we will use our guess values of 0, 0 and 0. Okay. So if we try to simplify this expression and we will continue. So this will be continued. So to get x2, x of 3, so these are iteration numbers till convergence. So you can check convergence by taking a difference between the last iteration value and the current iteration value. If that difference in the absolute terms, if it is exceeding a certain tolerance, in that case you can. If it is going below a certain tolerance, in that you can stop the iteration loop. Okay. So there are different types of ways to check for error. So you can take a simple error will be your absolute of the maximum of x at a given nth iteration minus x at a given n minus 1th iteration. Okay, so this is absolute maximum error, which means that you take difference, you will have a vector of all the values, you take the maximum and you take an absolute. Let's flip this over. So it will be absolute and then maximum. Okay, so you first take the difference, you will get a value set, all will be positives and negatives. You make it absolute, means that make it all positive, and then out of them whatever is the maximum you take that out, and that will be your error. And you want this error value to be less than certain tolerance, and the tolerance you can take any tolerance, say 1 e minus 6. Okay, so you can try to keep your convergence based upon your tolerance. You will have more iterations. So lower your tolerance, more will be your iterations. Okay. With that in mind, let's write down the expression for this. So xi of the kth iteration will be equals to 1 by aii minus summation j is equals to 1 to n I not equals to j aij xj of k minus 1 plus b of I. Okay, so let's see what we did. So we have this k minus 1 term. We will be summing over all the aij values except for I not equals to j, right. So if I is equals to j, in that case we will not consider. Apart from that, we will take all these values. Okay, in a matrix form, if say ax equals to b, so a matrix into x vector equals to b vector, where a matrix is this big matrix a11, a12, a13 all the way to a1n, a21, a22, a23 all the way to a2n, then an1, an2, an3, ann. Okay, so you have this matrix. You can decompose this matrix into your lower diagonal plus upper diagonal, where the lower diagonals will be 0, 0, all the diagonals are 0. You will just have the lower diagonal value a21, a31, an1, an2, an3 and so on, and all the upper diagonal terms will be 0. This is your lower diagonal, and your upper diagonal will be just the other way. So all the diagonals are 0, a12, a13 to a1n, a2n to all the way up to n minus 1 n. Okay, and the lower terms will all be 0. Then the diagonal terms you understand, right? So the diagonal terms will be a11, a22, a33 to an. So you can add this up, and then we can write this. So L plus D plus U times X equals to B. Now we can then take this L plus U term, that is the diagonal term is the only term which contains the x of I, and that is the only thing that we are interested for the kth iteration. For the k minus 1th iteration, and all the other term, that is j not equals to I, right. So we have written all j not equals to I. So that is your, so your ith terms are only on the diagonal, and off diagonal terms are your L and U. Okay, so d of x for the k plus 1th iteration plus L plus U x for the kth iteration equals to B. So we can say that d of x for the k plus 1th iteration equals to minus L plus U of x for the kth iteration plus B. And we can take d to the left hand side and take an inverse. X for the k plus 1th iteration is to minus d inverse of L plus U x of k d inverse into B. Okay, we can take this as a matrix T as a vector C. So x of k plus 1 equals to T x of k plus C. Okay, so in the matrix form, we can solve this expression by the Jacobi method in this format. Okay, then the next one is our Gauss-Seidel. So our Gauss-Seidel approximation is a slightly different or a slightly modified version of our Jacobi. So let's take our equation set a11x1 plus a12x2 plus a13x3 all the way up to a1nxn equals to b1, a21x1 plus a22x2 plus a23x3, a2nxn equals to bn, to an1x1 plus an2x2 plus an3x3 plus annxn equals to bn. This is b2. Okay, so the same set of expression. The modification of the Gauss-Seidel over Jacobi is that if you are solving for, so we again start with the set of guess values, right? You will start with a set of guess values. You calculate the same formulation for x1, x2, x3, except that for x1 you will use all guess values. Now you have a value for the first iteration for x1. For x2, you will use that new value of x1 and then all the guess values from x3, x4 to xn. Similarly, for x3, you will use the new values for x1 and x2, and then you will use all the old values for x4 to xn, and so on. Okay, so let's write it again. x1 for the kth iteration equals to 1 by aii. We will have minus a12 x2 for k, a13 x3 for k, minus all the way up to minus a1n xn for k. So for the first one, it's all the guess values plus b1. For the second one, it will be a22. Now you already know x1 of k plus 1. These are all k plus 1. This is k plus 1 minus a21 of x1 of k plus 1. Then apart from that, we do not know any other value. So we will take all the guess values now. So a23 x3 of k minus a2n xn of k plus b2. For the last nth value, for the k plus 1, ann minus an1. Now we know all the above values. So an1 k plus 1, an2 x2 k plus 1 minus an n minus 1 x n minus 1 k plus 1, so k plus 1th iteration all plus bn. Okay, so we start with a guess value. So start with a guess value x of 0, then each iteration, then each progressive values take the updated xi minus 1. Okay, so xi for k for k is equals to 1 by aii summation of minus a from j is equals to 1 to I minus 1 aij xj for the current step value minus summation j is equals to I plus 1 to n aij xj for the k minus 1 plus b of I. Okay, this makes sense. So what we have is that we have taken the updated values for the I minus 1, and then we have taken the guess values or the last iteration values for the one that is I plus 1 to n. Okay, in the matrix form, we again have A matrix, X matrix equals to B matrix. A we have written as D plus, let's write it correctly. So lower plus diagonal plus upper times X equals to B. So we know that the lower terms or the lower matrix terms are in reference to the previous, means I minus 1, 1 to I minus 1. The upper diagonal terms are with respect to I plus 1 to n, and the diagonal terms are with respect to I. Okay, so with that in mind, so let's write it L plus D plus U of X equals to B. So we will have L, the lower diagonal terms x of k plus the diagonal terms for x of k, and the upper diagonal term which is unknown for k minus 1 equals to B. So L plus D of xk is to minus U xk minus 1 plus B. We can invert this. So x of k will be equals to minus L plus D inverse into U x of k minus 1 plus L plus D inverse of B. Again we can take this, say S, and this you can take as some D. So x k equals to S of x k minus 1 plus D. This entire term is D. Okay, so this is our Gauss-Seidel. Gauss-Seidel is slightly more accurate, or can reach to convergence faster compared to Jacobi. So this is an example. We have taken this expression 5x plus 1 plus 2x2, 5x1 plus 2x2 plus 3x3 equals to minus 1, minus 3x1 plus 9x2 plus x3 equals to 2, and 2x1 minus x2 minus 7x3 equals to 3. So we have we are trying to set it up. This method that I have done, this is our Jacobi iteration. So you can see that the XL is used for all values. Now in MATLAB there is a very neat trick. If you just, instead of this XL, if you write X and the same expression, then this becomes Gauss-Seidel. Why is that? Is because that your X is getting updated at each iteration. So updated with iteration. Since your X is getting updated, your old X values now are already getting updated with the new values. So if you, instead of XL, if you put in X, then you automatically come to Gauss-Seidel. Okay, now if you don't want to write this big expression, you can also do this. You can take this, so since your A matrix times your X matrix, if you multiply the first row with the first column, that is your A into X of the 1, and you want to subtract the I is equals to J term, that is AII into X of I. So that is also possible. That is this commented term below. So this is a quicker way. So you can see that algorithms can be developed in different ways. This Jacobi took 13 iterations. Gauss-Seidel will take 9 iterations to converge to the solution. And this is the exact solution. This is the approximate solution. Our tolerance is 1e minus 6. So with this, I would like to end today's lecture, and thank you for listening.